In this video, we're going to look at the Euclidean algorithm, which is one method for finding the greatest common divisor or greatest common factor of two integers. Before we jump into the algorithm, let's briefly talk about what a greatest common divisor or greatest common factor is. So, first off, a divisor is just an integer that, I'm going to say, divides another integer. So for instance, 2 divides 6 because 6 divided by 2 is 3. 5 does not divide 6 because 6 divided by 5 is going to give me, I'll say, 1 remainder 1. There's this 1 left over when I take all of the 5s out. And a factor is pretty much the same concept. So a factor is just an integer. For our sakes, we could talk about factors of functions, but for our sakes, an integer that can multiply into another integer. So for instance, 2 is a factor of 6 because 2 times 3 equals 6. 5 is not a factor of 6 because there is no integer 5 times x that equals 6. It has to be some rational number in this case. And finally, to wrap up this idea, the GCD or GCF, greatest common divisor or greatest common factor, is just the largest integer that is a divisor or factor of, for our purposes, 2 integers. I could consider more than 2, but we'll look at 2 integers. Alright, so that's what we're going after. We're trying to find the largest thing that divides or multiplies into 2 numbers. So here's Euclidean algorithm. Now I'm going to show this in 2 methods. One is going to be sort of very explained, at an easier level to attack to get your answer. And the other one is going to be more useful when I'm actually proving. So I'll explain it one way, show the example one way, explain it the second way, show the example the second way, and then I'll go through the proof that this does in fact get me the greatest common divisor. So what we do is this. So I'm going to say I want to find the greatest common divisor or greatest common factor of 2 numbers a and b. And I will let a be the bigger number. If I had the bigger number in this part, I just switch the 2 numbers. Okay, so first I will divide a by b and find its remainder. I'm going to call that R1. Now, I'm not going to put this in this step, but if R1 is 0, then b is the greatest common divisor. I guess I can write that down. So if R1 equals 0, the greatest common divisor is equal to b. If not, we continue. And now I will do b divided by r1 and find its remainder. And I'll call that r2. And as before, if r2 equals 0, then the greatest common divisor is going to equal r1. And I just continue until the remainder, I'll say the n plus first remainder equals 0, and that's going to tell me that the nth remainder is the greatest common divisor. So just divide, find the remainder. Divide those, find the remainder. Divide those, find the remainder until I get to 0, and the previous one is my greatest common divisor. So here's my first example, and I'll do it this way here. So I'll start off saying, okay, I want to find the greatest common divisor of a and b. This is bigger than that already, so I'll just have it in this order. And so I will do 186 divided by 78. And this divided through is 2. This goes into that 2 times. 2 times 78 is 156. Subtract. That's not the way the subtraction sign goes. And I get 2 remainder 30. So in here, now I like keeping a little list here. I have 186, 78, divided those, got to 30. So now I'll do 78 divided by 30. And 30 goes into 78 2 times. 2 times 30 is 60. Subtract. And my remainder here is 18. And now I do 30 divided by 18. And I'm going to go a little bit faster. It goes in one time. I will have 12 left over. So now I'll do 18 divided by 12. 12 goes into 18 one time. I will have 6 left over. And now I will do 12 divided by 6. That goes in there 2 times, remainder 0. And so the last integer before 0 is our greatest common divisor. Okay, so let's work it back now. Another way to see this. Instead of thinking this through as just division, I can use the remainder theorem that says for any 2 numbers, I can have, or any 2 integers, any 2 positive integers, I can have, we set up in yellow, so we have a and b. I can say that the larger number will be the smaller number times some other integer plus some remainder. Okay, and this Q probably for quotient, R for remainder. And so then I will take these 2 numbers and I'll say, okay, well, the remainder has to be smaller than this number, because if it were larger, I could take another whole out of it. In our example here, this remainder had to be less than 78. If it were bigger than 78, I could take out another whole 78 before then. So now, I'll say that b can be written as the first remainder times some other number, and now leave me with some other remainder. And I continue through this process. This remainder has to be smaller than the first remainder, so r2 has to be smaller than r1, so r1 can be written as r2 times some integer plus a third remainder. And this continues. And I do want to point out a lot of this work it parallels very closely to the work in a book by Joseph Gallion. It's a good book, cheap. I like it, so get it if you want it. But just know that not all this was created in my head. I read through it, and this is going to be following along a lot of what he is doing. Okay, so this continues until we get to a point where we have sort of the n minus second remainder equals the n minus first remainder times some integer plus the nth remainder, and finally the n minus first remainder will equal the nth remainder times some number plus 0. And this right here will be my greatest common divisor, greatest common factor. And this has to eventually terminate. So you're saying, well, can't this just go on forever? No. A and B are positive integers. And A, B, R1, R2, R3, all the way up to Rn are decreasing. Well, there's only so many numbers you can get to before you get to 0. It's strictly decreasing. I can't have the same number show up again and again. So this will eventually terminate. We will eventually get to our greatest common divisor. Worst case scenario, it's 1, and they're what's called relatively prime. So let's see this problem done that way. So now I know that 186 is equal to 78 times 2, which is 156, plus 30. I take the 78 and the 30 and say, okay, that means 78 is going to be 30 times 2. That's the largest amount of 30s that can go into 78, plus 18. And I take these two numbers. 30 equals 18 times 2, not times 2, that's a lie, times 1, because 18 only goes into 30 one time, and there's 12 remaining. And I take these two numbers, slide them over. 18 equals 12. 12 goes into 18 one time, with 6 left over. And finally, take these two numbers, slide them over. 12 will equal 6 times 2, with nothing left over. So our greatest common divisor is, so I'm going to put between 186 and 78 is equal to 6. All right, so proof. Why is this the case? Well, here's the idea. So in here, we're using this remainder, the remainder rule here. And if I look at this last line here, so since r sub n minus 1 equals r sub n times q sub n plus 1, this means that r sub n divides r sub n minus 1. R sub n is a divisor of r sub n minus 1. That's great, but r sub n minus 1 isn't a and isn't b necessarily. So we keep going. Okay, let me change colors. Now, since r sub n divides r sub n minus 1, then r sub n also divides this term. Because something that divides times more, well, it still divides it, okay? For instance, so let me put a little numerical aside here, I'll get rid of this in a second. Since 2, let's not do 2, since 6 divides 18, and goes in there 3 times, then 6 also divides 18 times 5, 90. Because it already went to 18, so this went into that 3 times, this goes into that 15 times. It follows through with that, okay? So it divides this, then divides that. This means that r sub n actually divides r sub n minus 2, because it divides this part and this part. There's an r sub n right there. And this actually continues. So r sub n divides r sub k for all k in the first remainder up to the n minus first remainder. So it just goes right up here, and eventually, from the same process, well, if r sub n divides both of these, then r sub n divides b. If r sub n divides both of those, then r sub n divides a, and therefore r sub n is a common divisor or factor of a and b. Okay, so that shows that it is a common divisor. But it hasn't shown that it's the greatest common divisor. We're not sure at this point whether there's something that is larger, sitting above r sub n, that also divides a and b. So that's where the next part comes in. So, suppose r is a common divisor of a and b. Well, suppose hasn't in it. Of a and b. This implies that r divides a and r divides b. Okay. Which means that, well, if a equals b times q1 plus r1, and r divides a and r divides b, then r divides r1. And then I can work my way down. Okay, so if b equals r1 q2 plus r2, and r divides b and r divides r1, then r has to also divide r2. Let me explain why for a second, okay? So let's just look at, let's say 10, okay? So I know that 10 divides, let's do 70, and 10 divides 380. Okay, so just as a little numerical example so people are with me on this. So in this formula, I would have 380 equals 70 times 5 plus 30. The fact that 10 divides 70 means that I can write this as 7 times 10. This is 38 times 10. And clearly this is 3 times 10, we know that, but it has to actually be a multiple of 10, because this being a multiple of 10, or 10 dividing this, multiplied by 5 means that this is 35 times 10. And the only way to get to 38 times 10 to have 35 times 10 is to have 3 times 10. So the fact that these two are divisible by r means that that also has to be divisible by r with that addition. This continues until we finally see that r has to actually divide r sub n. And that can only happen one of two ways. Either r is equal to r sub n, or r is less than r sub n for any common divisor, and therefore r is the greatest common divisor of a and b. as was to be shown. I hope this helped out. Feel free to comment below if you have any questions.